Hello, in this video we're in the simple linear regression setting and we're going to derive the test for the correlation coefficient. And very briefly, in the previous video 18 in this playlist, we said y follows a line with some error, but we added a restriction, or not a restriction but a condition, that the x's are also normally distributed. So normally these are fixed values, and the error epsilon, or the error term, is only one that we impose assumptions on. But in PV18 we said both x and y are random. So the conditions are that epsilon is IID normal 0 sigma squared, and we're assuming a distribution because we're going to do a test. The x is normally distributed with some mean and some variance. Epsilon and x are independent, and that implies that y is IID normal with some mean and some variance. And we derived all these in the previous video. So essentially, f of x, y is bivariate normal with these means, these variances, and this correlation. And when you do simple linear regression, we think that this x helps us predict y. And that's why we do simple linear regression. And we want to know, are they correlated? Meaning, is x really helping us predict y? And that's why we're doing a test for the correlation coefficient. If this is 0, it says x and y are uncorrelated, so x doesn't help us predict y. So that would be a good thing to know. But before we get into the actual test, we need this property here. So let's show that t, which is this, r is the sample correlation coefficient defined in PV18 in sample size r squared, is equal to this. And this right here is the least squares estimate for beta 1, and this is divided by its approximate standard deviation of this. And this was actually the test statistic that we used in testing whether the slope was significant or not in simple linear regression where x was fixed. So again, this sigma squared hat is the estimate for the residual variance, or the error variance, and so it's the sum squares of residual over n minus 2. SXX is the sum of xi minus x bar squared. So now we start filling in information. So t is this, the sample correlation coefficient is this, SXY divided by SXX over SYY. These are actually the maximum likelihood estimates. So this is the maximum likelihood estimate for R. N minus 2 is the same, and then we do the same here, but it's squared, so it's essentially this squared. Now, in this case, the n minus 2 is the same, the divided by SYY is the same, and then we kind of move this piece to the top, but we multiply it by 1, which is the square root of SXX divided by the square root of SXX. So that's why we get one of those. So nothing really changed between the numerators. Denominators, we're going to try to find a like denominator. So 1 is SYY over SYY minus, we take this piece to the top, and since that's squared now, we have to multiply, so it cancels one of those. We only want 1. So nothing's really changed. Now the next result is from previous video number 3 in the list, where this numerator right here, this right here is the least squares estimate for beta 1, right? The same. Here, we just make it a fraction, so it's this, and that's the least squares estimate for beta 1, so it's squared SX, so nothing changes. Now, in previous video 8 and previous video 18, we use properties from them to go from here to here. Now notice that the square root of SYY cancels, so it just cancels. So now the numerator, of course, stays the same. Now SYY is exactly what we were calling SS total before, and PV8, we derived that this right here is actually the same as the sum of squares regression. Then, so now we have equal. So the n minus 2 we take down. Well, the total minus regression is actually the residual. All right, everything else is the same. This right here is the sum of squares residual over n minus 2. That's the unbiased estimate for the error variance. So and since it's square root, we'll just put sigma hat, and then that we take down. Well, that's what we wanted to show, right? That this test statistic is the same as this. And we've studied this when we're developing tests for beta 1, right? So they're equal. So what did we figure out about this? So from, a little background. From PV18, we derived this relationship. So this implies, and since this is standard deviation, that's the standard deviation of y, they're always positive. So if rho is 0, that means beta 1 is 0. And actually, if beta 1 is 0, then rho has to be 0. It's an if and only if. Okay? So this right here from PV12, if rho is 0, meaning beta 1 is 0, and we were in the x fixed scenario, simple linear regression where x is fixed, so beta 1 is 0, x is fixed, then this right here had a t distribution with n minus 2 degrees of freedom. And now we can write this like this. So if t is this right here, but we condition on the x's, that's saying fix them. Remember, x and y are random. So if we condition on x, that's saying fix the x's. Well, that means this right here is a t distribution with n minus 2 degrees of freedom. Okay? That's how we derived it. But note, when you condition on the x's, what's left actually becomes a function of the x's. But note that whatever x's we pick, it's still t with n minus 2 degrees of freedom, no matter what x's. So the distribution actually ends up being independent of the x's that we pick. So the distribution of the conditional t given x is independent of the x's, which implies that the distribution of t and t given x have the same distribution. So then our test statistic, we want to test is rho equal to 0 versus not equal to 0. Our test statistic is t, and under h naught, meaning rho is 0, we just showed that it's a t distribution with n minus 2 degrees of freedom. And that means that the rejection region is if the absolute value of this is too big, and we pick the t alpha over 2 cutoff, which is equivalent to if this is a t distribution, that the rejection regions are both tails with alpha over 2. And that's it. That's the test statistic to test whether the correlation is 0 or not. Now, generically, we can test it for a specific value. Is the correlation 0.5 or 0.2 or negative 0.4 with this test? Now, the test statistic is a z, and actually, this is the test statistic, and this is the mean of it, and that's the variance of it. So this becomes a standard normal. And now, it's approximate, so we need at least n equal 25 data points. And then we reject if z is too big, the absolute value of z, which is equivalent to going in the tails. Now, we're not going to derive this test statistic. And actually, I've never seen the derivation of it, but I know this from books and class, and I know that's the correct test statistic. Well, that's all I got for this video. Hopefully you enjoyed that. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.